Hello everyone, welcome to my YouTube channel Chemistry Quest. This is the 23rd lecture in solution series. So in this video we will be discussing vapor pressure of liquid solutions. Let's get started. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. When taken in a closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total and P1 and P2 be the partial pressure vapor pressures of the two components 1 and 2 respectively. These partial pressures are related to the mole fractions chi1 and chi2 of the two components 1 and 2 respectively. The French chemist Francois Martin Raoult (1886) gave the quantitative relationship between them. The relationship is known as Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. Thus, for component 1, P1 is directly proportional to chi1. Therefore, P1 is equal to P1 naught into chi1, where P1 naught is the vapor pressure of pure component 1 at the same temperature. Similarly, we can write for component 2, P2 is equal to P naught 2 into chi2, where P naught 2 represent the vapor pressure of pure component 2. According to Dalton's law of partial pressures, the total pressure P total over the solution phase in the container will be the sum of the partial pressures of the components of the solution and is given as P total is equal to P1 plus P2. Substituting the values of P1 and P2, we get P total is equal to chi1 into P1 naught plus chi2 into P2 naught. We know that chi1 plus chi2 is equal to 1. So we can write chi1 is equal to 1 minus chi2 into P1 naught plus chi2 into P2 naught. We can simplify and get it as P1 naught plus P2 naught minus P1 naught into chi2. Following conclusions can be drawn from equation 2.16. Total vapor pressure over the solution can be related to the mole fraction of any one component. Total vapor pressure over the solution varies linearly with the mole fraction of the component 2. Depending on the vapor pressure of the pure components 1 and 2, total vapor pressure over the solution decreases or increases with increase of the mole fraction of component 1. So we get a plot of vapor pressure and mole fraction of an ideal solution at constant temperature. The dashed lines 1 and 2 represent the partial pressure of the components. It can be seen from the plot that P1 and P2 are directly proportional to chi1 and chi2 respectively. The total vapor pressure is given by the line marked 3 in the figure. This line is the P total, which is equal to P1 plus P2. A plot of P1 or P2 versus the mole fraction chi1 and chi2 for a solution gives a linear plot as shown in the figure 2.3. These are shown by the dotted lines. These lines pass through the points for which chi1 and chi2 are equal to unity. Similarly, the plot of the line 3 of the P total versus chi2 is also linear. The minimum value of P total is P1 naught and maximum value is P2 naught. Assuming that the component 1 is less volatile than component 2, that is P1 naught is less than P2 naught. The composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the components. If Y1 and Y2 are the mole fraction of the components 1 and 2 respectively in the vapor phase, then using the Dalton law of partial pressures in the general form, we can write as Pi is equal to Yi into P total. So if I have to write for component 1, I will write it as P1 is equal to Y1 into P total. So this is about the concept video of vapor pressure of liquid solutions. I hope you enjoyed the video. So if you like the video, please hit the like button, share with your friends, subscribe to my YouTube channel, and don't miss to hit the notification bell for upcoming videos. Thank you and have a good day.